So let us start. So I'll continue the topic called pros and contras of Feynman integral. So first I'll speak about pros in the simplest model. And this is oscillator. By the way, piece of the art of mathematical physics is to find simplest models. Okay? And then we will go to the model that would be Lagrangian d phi star d phi bar plus lambda phi square phi bar square in or for dimension of x equals 4. And this is a Higgs model. So what is interesting about this model is that here we will describe why Feynman definition of local observable should be modified. And we will describe point B. How problem of of divergence is solved if we use definition of local observable coming from functorial approach to quantum field theory. Okay? So you may ask why I consider this model and dimension x equals to 4. Not because our world is 4-dimensional. It's just because it happens that it is the simplest model. Okay? It just happens that it is the simplest model. And point 2 is, of course, contrast. of Feynman approach. So I don't want to be shy. I want to make a clear statement. Feynman's approach is outdated and should be replaced by a new approach. I want to stress it, that I'm not saying that functorial approach is equivalent to Feynman. No, I'm making a stronger statement. Functorial approach is better because it has no ultraviolet divergence. Feynman approach has them, but they are artifacts of Feynman approach. And this would be the main message of my today's lecture. Well, so that's why I just want to conclude very briefly the harmonic oscillator. Oh my goodness. I will just remind that action is dx over dt square minus omega square, so it's an action, x square dt. Xn, sorry, x of t is sum over n, xn exponential I t over t n. So action is just t x naught square omega square plus sum over n greater than 0 xn moduli square and what do I have here? And here I have the following expression. You see, I plug it, I take derivatives. And here I have t. Here I have n square over t square plus omega square. Okay, maybe here minus. So I produced computation last time. Now integral is this one. So this n belongs to z. And here, so this is the measure. So this measure could be multiplied by some mu of t that we don't know a priori. And here I have exponential I h s. So what would happen? I will take Gaussian integral. So when I will take Gaussian integral, I will have a product. And here I'll have n greater than 0, 1 over n square minus omega square t square. And here I'll have something like, I'm sorry, I think I need to change my camera so you can see me. Mu of t and here I have t to some power. Yes? So I have this terrible product. What does it mean? Interesting. What does it mean? So let me even put, okay, no h's, no h's. So what does it mean? It is something weird. So this product does not exist in mathematics. So how people treat infinite products in mathematics? We don't know what the infinite product means, but we may study, let me call it I. Let me study logarithm of I. So it's logarithm of mu of t plus. Now good thing is that I have a sum.
Minus.
So this is divergent theory. No mathematical meaning. So what can we do? We can say that logarithm n square minus omega square t square is actually logarithm of n square plus logarithm 1 minus omega square t square over n square. Right?
I'm sorry, but shouldn't we say it like some other way? Because, well, it's divergent. This logarithm is divergent, but it tends to minus infinity. And when we exponentiate it back, we apparently get 0 for I, which is logical since we take a product of smaller and smaller values.
You see,
So does it mean that this value is not what we're looking for?
yes, this value is not what we are looking for, because what we are looking for is so-called partition function of the harmonic oscillator, and we will reproduce it in another way. So we are not ready to say that it is 0, okay? We assume that harmonic oscillator is a reasonable quantum mechanical system. So the 0 is not the answer that we would like to accept. So after I write it like this, I have here logarithm t plus logarithm n squared. So this is something divergent. I just want to show that it is really divergent. But you may say that...
Or should it be minus log n squared?
Minus log. You see, some signs are not important because they would disappear. Something divergent, but a function of t only. And there is also mu of t. that we do not know from the first principles of Feynman approach. Okay. So what we know about it? Known only up to multiplicative constant. So we just say that mu of t plus this infinite something is just some function mu tilde of t. And we want it to be finite. So here we already see some cheating, okay? Okay. But it is a section of pros, not a section of contrast. Okay, so if it is finite, then log of I is log of mu tilde of t plus sum over n log 1 minus omega square t square over n square. Ah, now this is good. This is a convergent theory. Okay. And probably I missed minus sign. Yes, I missed minus sign. Now, it means that I is what? So I is actually an infinite product of 1 minus omega square t square over n square. Times logarithm mu of t. Now, interesting thing is that what stands here is that this product is known to be a sine omega t so it is t times sine omega t. So this is mathematics. So the reason is that this infinite product has the same zeros as sine function. Okay. I say that 2 pi is like 1. I just don't want to take it into account. So this is mathematics. Now, the integral is 1 over sine omega t and here I have t times logarithm mu tilde of t. Sorry, no, now no, not log. It's mu tilde of t. And I'd like to call it mu 2 tilde of t. So this is my result. Okay. Result of functional integral after putting all infinities into mu of t. Now let us compare it with expected raise e to the ith. So let me take h Planck constant to be equal to 1 for simplicity. It is the sum over n e to the it en. Sorry, I need to put a capital T here. Here, en are eigenvalues of the following operator. Okay, so eigenvalues of the following operator are known. And we discussed it last semester to be omega, sorry, okay? So I plug it in the formula to get sum over n Okay. But here I see geometrical progression. And this is actually so up to coefficient 2. So this is 2 over sine d omega over 2. So now I can compare these formulas. Okay. So most probably I made a mistake here, and here is over 2. So formulas are the same. So pro of Feynman integral is that it really gives a correct answer for harmonic oscillator. Contra, it is that mu of t is divergent. Okay. So here I would like to make a logical pause, okay? Because, but before this logical pause, I would like to ask for questions. Tim,
Well, I have a question.
yes, please.
So when we compare the result of the functional integral with the usual partition function, we calculate this sum, and well, in a way, it also is not very convergent. The sum of exponents. It's or is it okay to? Well, I understand that the formula gives 1 over sine, but
Okay,
when,
actually, it's very convergent. It is very convergent. Okay, to make e to the minus ith convergent, consider imaginary
No, that would work.
limit.
That's obvious. Yeah.
Yes, and no problem in functorial approach. So sign would go to Finch. Okay. Still, there are ultraviolet, I would not say problems, peculiarities. In functional integral or Feynman integral. So look, if we have these peculiarities in such a simple system in dimension 1, how can we dare to say that we can quantize curved multidimensional system, and especially such interesting systems like gravity? So here let me give a very physical remark. Okay. Suppose we would like to do the same thing for, say, Hilbert-Einstein action. That depends on G. This will be a metric. From the Feynman point of view, we should put here some measure. On a infinite dimensional space of metrics. Note that it is not just product of G of dg mu news. Let me advocate this. Why it is not just this product. We need to keep invariance with respect to general coordinate transformations. So actually we are integrating not dg, we are integrating dg over diffeomorphism. And this is curved space. Like c square over c star is cp1 that it is curved. And of course, we will have peculiarities in functional integral. So I just want to say that functional integral is not a very nice prescription. So actually, I'm having a seminar in Russia about it. But here I just want to make this remark. So here, but this was in the section of prose of Feynman integral, okay? And after the break, I'll come to contrast. Let me continue. So problems. I'm coming to my section 2. Problems in Higgs model. On R4. So action is an integral over R4. And here I have d phi star d phi bar plus lambda phi square phi bar square. So task. Compute an integral of something like phi of x1, phi of x2, phi bar of y1, phi bar of y2 as some function of x1, x2, y1, y2, lambda, and h. A. If xi is not equal to yj and lambda equals to 0, it is not a problem. And f is actually plus or actually minus actually there is a minus sign here, but it's not that important. I think there is a minus sign.
If there's a minus, then x1 and equal to x2 would give 0. Is that the expected behavior for boson field?
No, it's a plus here, sorry. Now, Let us inspect what happens if x1 equals y1. From Feynman perspective, there is nothing wrong in it. Phi bar is just a function, local function. Actually, a result diverges. So something is wrong in Feynman definition of local observables. They are not just functions of phi, d phi, etc., evaluated at point x. So there is one thing that I don't like. I don't like political correctness. If something is wrong, I just say it is wrong. Otherwise, we will not be able to do science. So why this is a problem? It is because the first deformation in lambda is integral d phi and here we integrate over x in R4 phi square phi bar square at x. And here we have our phi of x1, etc. But this is divergent. Okay, you see, it's wrong. We cannot use it. So those who know diagrams say that this divergence comes from this diagram, two loops. And here we have green function, and here we have green function. But it's just a picture. And problem is that gxx does not exist. You see, if we just say it's infinity, it would not help, okay? Infinity, we are not compactifying the values by infinity. The way to say that it is just a constant and could be ignored or reabsorbed also doesn't work. Because this also does not exist. Okay? Thus, functional integral has to be improved. Okay, people say improved. I would like to say modified. Prescription. I will call it functional integral prescription. And here, functorial approach comes. He says, local observables are a derived object obtained in the following way. I gave this definition, but I will repeat it. I'm sorry. I think I need to have more space. Consider a disk and another disk. Let this be R2 and let this be R1. So main object is functor applied to this thing belongs to homomorphisms between vector spaces V1 and V2 associated to spheres of radii R1 and R2 respectively. Here I wrote them as circles, but you should understand them as disks, okay? So this is actually a ball 4. Now, local observable is a function is a state valued function psi R1 that belongs to V1. Such that limit when R1 goes to 0 let me call it F of F psi of R1 exists. Such limit would depend on a state valued function. Moreover, different can give equal limit. So we identify them. Okay, so this is a definition. So in some sense, local observable in quantum field theory is like velocity in or like tangent vector in differential geometry. Analogy. In differential geometry, tangent vector is an equivalence class of maps 0, 1 to manifold X such that gamma of 0 is X0 and gamma is equivalent to gamma tilde if so I hope you know it from differential geometry. So these psi r's are analogs of gammas. So what I gave you is a mathematical definition that explains the following picture. that local observable come from a limit. Sorry, maybe this picture is not good enough. Of a sphere collapsing to a point. It's not a point. It's a sphere collapsing to a point. Now, I want to make two statements that we will explain later on. As two formulations. As functional integral, so it is just analog of harmonic oscillator. And as a functorial. Analog of e to the th. We will prove it later. Statement 2. Phi of x in functional integral is also an observable in functorial. We will prove it later. But now, construction in functorial QFT. Functorial QFT. It is called OPE, historical name. Given two local observables, one can construct infinitely many new observables by the following procedure. That I'll describe. And we will see the actual meaning of phi bar. Okay? So here I'll draw some pictures. So this would be R2. This would be R1. I'll have this point. And I'll take another point. So this point would be 0. This point would be that I will call R1 over 2. Okay. Then what I'm going to study is functor applied to and here I have observable O0. And here I put observable O1. And this functor belongs to, sorry, I call the space V, to VR1. Okay. And then I will try as psi R1. Okay. Is it a good vector valued function? Of R1? It's my question. So different things could happen. That when R1 goes to 0, there is a limit. Example. O0 is phi, O1 is also phi. Phi of 0, phi R1 over 2 has no singularity. As R1 goes to 0. So the state valued function has a limit that corresponds to phi square of x that is well defined even in Feynman picture. Another example. O0 is phi, O1 is phi bar. Then this function behaves like 1 over R1 squared plus regular terms. So I call it phi bar. So f of phi bar is not a function corresponding to local observable. However, if I subtract singularity, then f phi bar minus 1 over R1 square f of nothing has a limit when R1 square goes to 0. Such psi R1 is defined as phi bar double dots. Not is defined, I'm sorry. It's called in literature okay. One problem solved. Phi bar is a bad object. Phi bar with double dots is a good object. Later on, we will play more with this construction. So in particular, correlator of phi bar double dots at x phi at x2 phi bar at y2 is 1x minus y2 modulo square 1 sorry, I said I did it wrong. x minus y2 moduli square x2 minus x moduli square. Just this, just one term. Okay?
What about, shouldn't we also have a singularity when x2 approaches y2?
Yes, but here x2 is not equal to y2.
Yeah, but this
just
expression is not singular at x2 equals to y2.
so it means that I made a misprint. So it has x y2. Okay. So let me see how to correct it. Okay, 1 second. So I just want to say that in this expression, okay, maybe I was wrong. This x2 and y2, you see, here there is no constant there. No, so I wrote it properly. It is x minus y2 moduli square and x minus x2 moduli square. So coefficient in this coefficient in front of this singularity is 0. Tim? No, I got it right.
It's unclear. So we can just put x2 equal to y2 and everything should be fine?
No. You see, here I am writing it without proving it. Okay? I gave you a procedure. So if you do this subtraction, that's what I think you would get. Okay. Okay, maybe I'm wrong. Let me redo it together with you. Okay?
Can you scroll up to the place where you originally wrote down this yeah, here there's a term that contains 1 over x2 minus y2 squared.
Yes.
I can't see how it can.
But now but now we subtract something like x1 minus y1 with coefficient 1.
All right, I guess.
So we are discussing this term, right?
Yeah.
But when we are writing phi bar in double dots, we are just subtracting this term. Okay, let me write it down explicitly to show you what we are subtracting. Okay. So what does it mean? Okay, why? It's because we have phi x1, phi bar y1, phi x2 phi bar y2 minus 1 over x1 minus y1 square phi x2 phi bar y2. Okay? So first we do this, and then we consider limit y1 going to x1. So let me remind you, what is phi bar? Okay? I hope you see that psi r1 is this thing where we subtract 1 over their difference divided, and we put here nothing. Okay? So here is the definition of phi bar double dots. It is a definition. So I apply it here. I am getting this. And it means that I have just x1 minus y2 moduli square, x2 minus y1 moduli square, and then I have a limit, y1 going to x1.
Yes, I see it now. Yeah.
Okay, so thank you for asking before, because some things have to be explained. And I would say similarly, we may do it for phi square, phi bar square, okay? Wrong. Okay? Now, integral d phi e over d phi has a chance to be correct. Okay? But it is correct only in first order in lambda. And here I'm coming to the most subtle point. Red line. Now I'm crossing a red line. Deformation in the second order in lambda is an iteration of the deformation in the first order. So what does it mean? I will write it like this. Integral d phi exponential d phi star d phi bar. Here I put lambda 1, phi square, phi bar square. And here I put lambda 2, phi square, phi bar square. Okay? And I want to get term linear in lambda 1 and lambda 2. So once again, this is wrong. No functional integral exists. What is true? Is the following procedure. Deform theory by in the first order in lambda 1. Point 2. Recalculate local observables in deformed theory. Use new local observable to deform further. Okay? That's how we go. Analogy.
There's a question in chat about the meaning of lambda 2. Is it just our deformation parameter?
Yes. So analogy. Suppose we have manifold. And we have a point, x naught. So deformation in the first order is given by tangent vector. It's clear. How are we doing deformation to the second order? Is we need to transport V to the point x naught plus v. And then get x naught plus v x naught lambda 1 plus lambda 2. And here I have v at a point x naught plus lambda 1 v1 v. This is how we do it. Okay, so it's a subtle thing, and I just don't want to talk about it right now. I just want you to think what would happen. Just phenomena. Phi bar square double dot is not a local observable in deformed theory. Really. And here we have, in deformed theory, integral over a disk of phi square phi bar square. We again have divergence. So we need to recalculate space of local observables.
There's another question in the chat regarding normal ordering the entire exponent with the action.
Normal ordering of entire exponent, what does it mean?
Well, you can read the question. It's
Okay, I'm sorry, because question comes in one-to-one place.
I mean, you can put.
No,
Okay.
no. Okay, so once again, it is a very subtle phenomena, and we will discuss it in more details next time, because it deserves like 1 hour of drawing pictures and thinking. And here we will come to phenomena of their normalization group. I just don't want to jam it. Okay.
But what do you mean by adding a lambda 2 term? It's just lambda 1 plus lambda 2.
You see, lambda 1 plus lambda 2 means that I would like to do the deformation in steps. Second order, I consider second order, I consider deformation to the second order as deformation to the first order in lambda 2 of the theory that was deformed first order in lambda 1. Okay, so that's why I just want you to have a look at this picture. What do we actually mean by the second order deformation of a point on a manifold? Okay, I will draw one more picture. We have a point x naught on a manifold. It's not the source, it's just some abstract space. With the help of the tangent vector, we go here. What does it mean to what is a trajectory up to the second, up to the second order? So first we move like this. And then we know we need to move somewhere, okay? So I prefer to think about it in the following way. Base of deformation as formal series in lambda 1 lambda 2 and consider term in front of lambda 1, lambda 2. It is just more convenient to do this. Later you may say that we take lambda 1 equal to lambda 2 and term lambda 1, lambda 2 goes to equal to lambda, goes to lambda squared. However, conceptually, that's what I would like to do. I would like to understand deformation to the second order as a deformation of the theory that was deformed to the first order. Okay? And once again, it is exactly the place where we will meet the would-be ultraviolet divergences, and they would disappear when we treat things properly. So in what we discussed today, we found that one type of ultraviolet divergences in Feynman picture disappear if we say that terms in Lagrangians are not local observables. That if we deform by local observables, everything is fine and finite. We do not need to put anything like ultraviolet cutoff, or renormalize, or doing some other crazy stuff. This is just wrong. Okay? And it is wrong because it's based on the idea of the functional integral. And this is correct. And the next time, it would be on Thursday, I will get rid of the second ultraviolet problem, okay? And you would see that in the functional approach, there are no ultraviolet problems. Okay, now questions. Now it's time for questions.
I have a question.
Yes?
So what about the field phi itself? It is, as a local observable, it is correctly defined.
Yes?
But if we think about it in the same way, so it came from something that had a limit as the sphere, the radius of a sphere
Yes.
around the point tended to.
So later I will comment on it. I already wrote it as a statement that I'm going to prove later on. So when it was? Yes, there was a statement too, that phi of x in functional integral is also an observable in functorial QFT. And we will prove it later, okay? You may ask why I'm explaining it in this order. Because if I'll do it in the opposite order, namely, I will work out this phi of x in functorial and in Feynman, you would say that I'm just doing trivialities, because everybody knows that it works, okay? So let me go assuming these statements, and later on, I will prove these statements. Only after we will see that it is useful, you see? That it is useful and interesting. Tim, do you see my point? Tim?
Yeah. Yes, I do.
So first we need to know that something is useful. And if something is useful, then we may think, how can we prove this useful thing? Okay?